Okay, I think we're all back. So to finish our story, so I saw this and I was like, okay, let's see if we can figure this out. And I was like, there should be a connection between specific heat and density. I don't know what it is, but it seems like just looking at the data, there's an anti-correlation. So, so what I did, so we have our measured values are the points, and I made a little model for the density. And it was really, really simple. It was just the molecular weight divided by the mean molar volume. So the mean molar volume is, and it was kind of like you take all the atoms in your solid, and what is the volume of basically what's the average volume per atom. And you would think it would depend on whether it's hydrogen or carbon, but I was like, let's just start simple and figure out if we can assume that we have some kind of average volume. So how did I get the mean molar volume? Okay, so that's how I calculate the mean molar mass, knowing how many carbon and hydrogen atoms were in each molecule, and then I had to figure out how many molecules were in each unit cell for the solid, right? I need to factor in the time of delay here. And then I was like, okay, what's the molar volume per atom? And I just plotted it as a function of the carbon to hydrogen ratio. So how did I get that number, right? So this is where I was like, okay, I gotta figure something out. So it turned out that all of the ones that I included here in this study, where a lot of the ones that I found specific heat and density for, I actually also found X-ray crystallography data for. So here's the mean molar volume is a function of the unit cell times Avogadro number, just to convert from moles to number of atoms to moles, time divided by the number of atoms per molecule times divided by the number of molecules per unit cell. And a unit cell is, if you've ever taken a class where you've looked at crystallography, you'll notice that, you'll remember that a crystal can have different shapes depending on how the molecules or atoms align with each other. And these are the basic types of shapes, the monoclinic, the orthorhombic, and the triclinic. So it turns out all of these molecular species I found had one of these three types of shapes. And if you look in the X-ray crystallography data in the papers, they actually tell you what the shape is. In fact, they tell you basically everything you need to know. You just have to figure out what the language is, like what they're actually saying. So, so here are what the different shapes look like for these different molecular species. So these are all images from these different papers that people have published, and most of the data I found was from 1950, like in that range, 1945, 1950 to 1955. These are all really old papers, and I was like, wow, there's tons of data here. There's tons of information. It must have been the time when people figured out how to do X-ray crystallography of these types of materials, and then they just did a whole bunch. And if you look in the old literature, it was all when they were trying to figure out how toxic they were. So it was tied to the funding was all coming from places that were paying them to figure out the toxicity of these different molecular species. So I just happened to stumble on a gold mine and just started plunging into figuring out how to use all the data. And it was a really cool. I was I had papers all over the place. I was like trying to figure all this stuff out, writing all the numbers all over the place. Back to this guy. So I figured out the density, like with that simple equation. So I was like, okay, well, there has to be an association between the specific heat and the density. And this, if you remember from your thermal classes, this is the specific heat is relative to, remember, weight, grams, so like per gram, right, of weight of the, or mass of your material. And the heat capacity, the molar heat capacity, is relative to the molar in the number of atoms you have in your material, right? So there's a correspondence between the specific heat in grams and the molar heat capacity. So that is just the density. So now we can go back. We know what the density is. So I substituted here in this equation the density times that volumetric heat capacity. Well, it turns out 5 minutes from now when this comes up, that volumetric heat capacity is constant. So we can just use a constant and put that into the equation, and now we have the specific heat for these species as a function of carbon to hydrogen ratio. Okay, so now you can start thinking, oh my gosh, well, how would I use that? Say you're doing a model and you're trying to you wanted to calculate like how your soot is evolving, you're modeling soot formation. And you start to get inception. You start to get these molecules are starting to form. Then you can go, okay, once I get to a carbon to hydrogen ratio of X, I'm going to say that has a density of this. And then you can evolve the density of your particles as they grow, right? So as you get rid of the hydrogens in your model, you have that mechanism down, you're going, you can get rid of your hydrogens, right? So now you can calculate for your model the different thermodynamic properties. You can also use this, so then I took those equations and I propagated them out and I said, okay, let's go out to see what it looks like when we actually have a soot particle. So that's and we start to have mature soot. What happens when we have mature soot? Can we compare this to polycrystalline graphite? Can we compare it to single crystal graphite? Okay, so here's the graph. It actually, notice the bottom is a log scale. It actually works all the way out to graphite. So I was like, oh my gosh, this is just amazing. So I was just so excited. I was bouncing into my radiation treatment, like, oh, this is like great day. So here are the equations. They actually work. Okay. Come on. Okay, there's our graph, our polycrystalline graphite, our single crystal graphite. This, I put soot on there. There are a couple measurements for the density of soot, right? So that's on there. See where it actually goes on the line. It's like awesome. Like I actually got it to work. So okay, I got to calm down here. Now we can use this. We can use the data. Okay, look at our success. We can use the data to compare to measurements. And this is, so that was as a function of our composition, right? So carbon to hydrogen. We're in a flame. We actually want to know what's happening inside the flame at high temperature. So all the data were taken at low temperature. Can we actually now get these relationships as a function of temperature? So how do we do that? So we can so here's density as a function of temperature for graphite, right? For polycrystalline graphite and for single crystal graphite. And you notice that we actually have a relationship. So this is all tied to the thermal expansion coefficient, right? Thermal expansion coefficient will tell you how much a material changes, how much it expands when you heat it up. That is tied to density, right? It's just 1 over density. So we have these, I shouldn't have put so many animations in here. Okay, so this is the relationship we have that we get from graphite for the thermal expansion coefficient. And we can actually use that thermal expansion coefficient and calculate what we get for different carbon to hydrogen ratios based on starting point and just expanding it as a function of temperature, right? So then we calculate for different carbon-to-hydrogen ratios, starting from incipient soot, moving out to like mature soot, graphite. We have it all there. So that's how we can calculate. Now we have density, specific heat as a function of carbon-to-hydrogen ratio and temperature. Okay, so there we are. Yes, and then let's see. Can we use this and connect this to measurements? Like, so if I make a measurement, can I connect this? Okay. This is wait. Come on. Okay, so I can. Okay, so that was for density. We can do this for specific heat. I'm not going to spend a lot of time on this, except the computer wants to. Okay, yeah, we got it. Okay, so we can do this for specific heat using graphite as a proxy, the functional form for graphite, and then do the same thing for the specific heat. No problem.
Actually, if you give it this,
Yeah.
turn it to me and then.
Excellent, thank you. Yeah, no problem. Okay, so here's here's our specific heat as a function of temperature. Thank you. Okay, so we got this down. Okay. Oh, if I turn the laser pointer off? Oh, that would, thank you, Dalton. I think I can do that here. Did I turn it off? Okay, so let's connect this to, I turned the laser pointer off, so that's good. So let's connect this to measurements, right? Okay, remember yesterday I said we can measure the dispersion exponent, right? Or the angstrom exponent, whatever you want to call it. That exponent up there that tells you the Xi, I think, I don't know how to say it. Yes, Arvind, yes, what?
If you go back to the previous slide.
Yeah?
My question.
Oops. Oh. Okay, wait, let me go back. I'm trying to go back. Okay, yes. Does single crystal graphite what? Oh, does the morphology change when you change temperature for graphite itself? So graphite so it's interesting because the morphology, so the fine structure of single crystal graphite, what happens when okay, this is a really interesting point in materials. Graphite has these sheets of graphene. So you have a thermal expansion coefficient that goes like this, that's perpendicular to the basal plane, and then you have a different expansion coefficient that goes like this. If you look at polycrystalline graphite, there are two expansion coefficients that will have an impact on the specific heat. So you can plot this, perpendicular or parallel. That one, I can't remember if it's perpendicular or parallel, or it's just an average of the two. I can't remember which one it is. It might be an average of the two. But polycrystalline graphite will be right in the middle, right between the two. So polycrystalline graphite is just crystallites that are kind of randomly oriented. Does that make sense? So soot is like a polycrystalline graphite, much more like polycrystalline graphite. Yeah. But that one's for single crystal graphite, and I think I probably took an average if I found two. Or it might just be that it's I can't remember, but it might just be in the literature as that one curve, yeah. Okay, now let's see if we go. Okay, so we have this dispersion exponent. We can measure the dispersion exponent. And we have this correlation. So if we know the dispersion exponent, we can infer the carbon to hydrogen ratio. If you can measure the dispersion exponent, right? Remember I showed you the multiple times now, like maybe 3 times, I showed you the dispersion exponent for that one study as a function of height in the flame. We can actually measure the dispersion exponent. There are different ways of measuring it, and we'll talk about that in a little bit. You can either measure it with extinction. That's harder to do because you have absorption and scattering. Or you can measure it with a technique that's explicitly dependent on absorption, so like laser-induced incandescence or photoacoustic spectroscopy. Or multi-wavelength, so the dispersion exponent you can get it from multi-wavelength LAI or photoacoustic spectroscopy. And then temperature, and then you also want temperature, right? Because you want to know in the flame as a function of temperature. You can do that with a whole bunch of different spectroscopies. So we'll talk about that in a little bit. So now you can make a measurement of flame. You don't have to put a probe in there, and you can get these thermodynamic properties. At least estimate them, until someone figures out that's wrong too. But let's assume that it's right. Let's hope that it's right. Okay. Okay. Yes. Okay. Right. Let's go. Okay. I don't know. It's still darn slow. Okay. So there's our whole equation for density. Here's our whole equation for specific heat. And then here's our volumetric heat capacity. Okay, so let's talk about surface growth. There are 2 basic mechanisms for surface growth that people talk about. One is that you have sequential growth on the surface of through the Haka type mechanism, right? So you have this graphene type sheet on your surface, and you get hydrogen abstraction from one of those carbon atoms, an acetylene addition, and then you get hydrogen abstraction, another acetylene addition, and then you close the ring. So you basically grow the rings on these sheets on the surface. So you basically grow these sheets out. So you get these bigger and bigger conjugation lengths of the stuff on the surface. That's one way to add carbon to your particle. Another way is to, so this is the Haka mechanism. Another way is to actually add, so there's the Haka mechanism. What's going to happen is you're going to grow the graphene sheets. Another way is to actually just add whatever's in the gas phase is just adsorbing to the surface. And then whatever it's doing, once it hits the surface, it's doing, it's reacting or whatever. But so you have these gas phase species flying around your particle. They attach the surface somehow, maybe through a radical mechanism, we don't know. And then they stick to the surface and they add to your particle. So that's another way. So what we want to do is figure out, can we get some information to figure out what kind of mechanism? And then different mechanisms could be happening under different conditions. Okay, so what we did is combine a number of different types of measurements to see if we can sort out what's going on. So we have this, we have we can make these measurements of particle maturity using our dispersion exponent, right? We used laser-induced incandescence, which is a technique where you don't have to worry about scattering because you're only sensitive to absorption. So you take a high-powered laser, you send it into your flame, it absorbs the light. We use 1064 nanometers, which isn't absorbed easily by the other species running around the flame. So the particle absorbs the light, heats up, and then we look at the emission, okay? And then we change the laser wavelength that allows us to get a wavelength dependence, and then that gives us the dispersion exponent. Okay, that's how we got, so here's our flame, so I'm gonna show you some results. Here's our flame, it's what we call linear Henkin burner, so it's a Henkin burner, which is a whole bunch of like hypodermic needles sitting in a honeycomb. So they're really tiny little microjets of fuel, and then the honeycomb is where your co-flow of air is going, so you basically have little tiny diffusion flames. We were doing this experiment, we designed this burner for some experiments we were doing at a synchrotron where we had very little space. So we made a little teeny tiny burner, and we did it in a line. So we had these little hypodermic, like 15 or 25 or something, little hypodermic needles sitting in a small honeycomb section. Okay, so it made a linear flame. So we're looking down the side and then down the end and then along the side. And this is the laser-induced incandescence as a function of height in the burner. So on the bottom is volume fraction. So as you go up in the burner, I made it exactly the same height as that picture. So you can see that as you go up in the burner, laser-induced incandescence actually measures, the main reason people use it is to measure volume fraction of soot in a flame. It's just linearly dependent on the amount of incandescent signal. Okay, so we measured how much soot you have in the flame. Okay, the one thing to remember about LAI is it's usually, it's sensitive to mature soot. So the soot has to absorb strongly in order for you to get enough signal for it to, and it can't vaporize. It has to go up to pretty high temperature because it's dependent on temperature of the fifth power. So it has to go to pretty high temperature to get adequate signal. Okay, so there's our extinction, and we used LAI to get the dispersion exponent. So that blue curve is the dispersion exponent. The pink curve you can also get from LAI is that beta parameter and the cross-section and calculation. I won't go into that right now. We'll talk about that later. But they're anti-correlated, and they both tell you about the soot maturity. But remember, dispersion exponent goes down as maturity goes up. Yes, a question? Oh, so I think your question is, what is the error associated with the measurements? And I didn't put error bars on the measurements, right? That's a really good question. I'm not exactly sure how to assess the error, the full error, because there's a lot that goes into evaluating that dispersion exponent. I would say it's probably on the order of 10 to 20%.
Yeah, because we use our.
Yeah, so if you do LAI at 2 different temperatures, you can get the dispersion exponent. Yeah, definitely. Yeah. So, and then we calibrated the LAI signal for volume fraction with extinction. And we used the dispersion exponent in the extinction measurements to get the absorption cross-section, so we knew what the extinction was. So we basically used both to get the volume fraction. Okay, that was a good question. Okay, so we kind of have a measure of the maturity. And it's stuck in my computer. Okay, here we go. So the next thing we did is we did a study where we took that little burner to a synchrotron and we did small angle X-ray scattering. So small angle X-ray scattering, or SAX, should be sensitive to the incipient particles. It's short wavelength. We should be able to see the incipient particles, though I don't think we really can see the incipient particles based on some of this analysis I've done recently. I think we need a better technique. But we do have some sensitivity to the less mature particles than what we have sensitivity for with LAI. So we did that. And we extracted from the flame and did TEM, transmission electron microscopy, and got the size of the primary particles, both the size of the primary particles and the aggregate size from SAX, from the SAX measurements. And we'll talk a little bit more about that later. Okay. Okay, so here are some of the TEM measurements. So you see that in the middle we have what looks like mature soot, and so at 5 and 7 millimeters above the burner, we have those big stringy aggregates that we were talking about. That's what mature soot looks like. And that's where we see the strongest LAI signal, and it's pretty flat, right? At lower heights, our LAI signal goes away, and then we get this globby, like big globby thing. I think those are, when we extract, we get coalescence or like coagulation of the particles. They kind of stick together in our sampling. I'll talk about how we did the sampling a little bit later. And then at the top, that's where we get oxidation, the particles go away. Okay, so the particles are small, LAI signal goes away, and the TEM images get tiny. Okay, this is what the Sachs signal looks like, and we see Sachs particles lower in the flame where the particles are less mature. Where we don't see LAI, where the LAI goes away, we see Sachs signal still. I think that's because of the difference in sensitivity to the less mature particles. Okay, so the next thing we did, okay, so we developed a core shell model for analyzing the Sachs data, and this is what the core shell model gave us, is we actually have, it's inversed a little bit, like we actually have core shell structure in the middle of the flame, and then we have homogeneous particles, so that one means that we have homogeneous particles at the top and bottom where we have oxidation, we oxidize away the surface, and on the bottom we just have, homogeneous incipient particles. I think that's what that is, but I still am thinking about this. It's kind of a new result. Okay, come on. And then growth of the particles. So this is where we see all these species in our aerosol mass spec is down low in the flame where we see growth of the particles, okay? Okay, we also did XPS, and that's that blue curve right below the pink curve. So you have LAI, which gives you an indication of the maturity, and then the XPS XPS is a surface sensitive. It's just surface sensitive. So LAI is bulk sensitive. So it's sensitive to the material, the entire material of the particle. It tells you the maturity of the entire particle. XPS is only sensitive to the surface. So it, like the top nanometer or so. And what we see is defects that are higher on the surface of the particle. So basically we did, what is the maturity of the particle? If it has high defects, then the maturity is lower than if it has fewer defects. So we plotted that, our defect ratio. And the maturity of the particles from XPS, it goes up kind of like LAI does, but it takes a couple extra millimeters to get to our highest maturity on the surface. And I think this is because as you're adding, if your ions are drifting around in space, we see the same distribution of types of species. You'll see that on the right-hand side as a function of height. The types of species don't change as a function of height. It's the same type of 4 to 7 ring type species. They're adding to the surface continuously. So as the bulk is maturing, the surface is not maturing because it's just growing with these non-mature species, these kind of constant size species. So the maturity would be how big is that sheet. So what it looks like is that we're not getting, in this flame, in this region where we did all these measurements, we're not getting the growth of the big sheet on the top because that would make our surface maturity grow faster than our bulk maturity, but our bulk maturity is actually growing faster than our surface maturity. So what I think is happening is that we're getting this mechanism, adsorption of pHs on the surface is what's causing surface growth. Okay, so so here's kind of a summary of what we think, all these things that are happening inside the flame. I'm going too slowly, so I need to move on. But okay, so let's talk about composition and maturity. So remember we talked about this result yesterday, this one where Hai Wang's group saw high aliphatic character in these particles, and this The aliphatic, so here's another figure that shows this, and as they go up in the flame, they actually see more aliphatic to aromatic character. So it's higher aliphatic to aromatic. Totally not what we expect. Totally not what other people seem to see. So that's one result. So we talked about that yesterday. This is actually really annoying, doing this. Okay, come on. Okay, and here's a different result. So in this case, they looked at the H to C, they did infrared spectroscopy, and they looked at which Hai Wang's group did, right? They did an infrared spectroscopy, the same type of experiment, and this is also a premixed flame, right? And what they saw is the aromatic to aliphatic ratio. So if you look at so H to C ratio on the bottom, so that I usually think of C to H, but H to C goes down, that means C to H goes up. That means there's more aromatic content in these particles as they go up in the flame. That's opposite of what I just showed you from Hai Wang's group. Okay, so this is, and the middle figure shows H's that are in aromatic rings versus H's in aliphatic rings from the IR spectroscopy. And notice how the aromatic stays high and the aliphatic goes down as you go up in the flame. So that's opposite of what Hai Wang's group was showing. So this is all like, we need to have better ways of doing this. So I challenge you, if you're an experimentalist, come up with good ways to make this measurement. Okay, so we go back to this flame and try to understand the composition. I think I skipped over something, but I don't know what it is. I think I got the orders, but anyway, okay, whatever. So let's talk about, so are there any questions so far on composition and maturity before we move on to oxidation? Okay. So here's a question. How would you define, if you have a particle that's oxidizing, so we're going to talk about oxidation. If you have a particle that's oxidizing, you've gotten rid of all your hydrogens, or a lot of your hydrogen, right? And you've become mostly carbonaceous. And now you have an oxidation mechanism that's like grabbing carbons from your particle. So your order, like you're getting defects in these, some of you have told me about some of your materials work that you're doing. If you're grabbing carbons from these graphene sheets, would you call that less mature? That's just a question I'm going to throw out there because I don't know the answer to it. Just that we could just ponder that one. Okay, so let's talk about oxidation. Oxidation is really important because if you think about it, if you have a process that's generating soot, right? If you oxidize it away, if you can generate a ton of soot. If you oxidize it away, it doesn't matter, right? So we really want to understand oxidation, how that happens. This is a beautiful experiment from Murray Thompson's group. This is the group that Mani Sarathi was in as a grad student. This is a really, really nice paper where they looked at oxidation of particles kind of in an environmental chamber. So they could watch oxidation. And their different studies have shown that sometimes particles are oxidized from the inside. So oxygen percolates into the particle and oxidizes the inside. And sometimes particles are oxidized from the outside, right, on the surface. So this was kind of a curiosity, and this is actually important if you're trying to understand how oxidation is happening. So they put these particles in where they could watch through TEM, they could actually watch the particles as they were oxidizing. So if you start out on the left-hand side and you move over to the right-hand side, you'll see that the particles are kind of disintegrating, right? They're going away as they oxidize. And you'll notice that, they're oxidizing in different pathways. So it turns out that particles that are not very mature tend to oxidize from the inside. So they did a whole bunch of studies with different types of particles. Here's one that shows that particles that are mature. So I just showed you one that the particles are not very mature, like it looked kind of amorphous, like you didn't see that clear ring structure. Here's one that shows that clear ring structure. So they put a circle around it, right? They started out on the left. And on the inside, you see the inside is a little bit disordered. There are a couple of little spots where it doesn't look like you have a strict ring structure. And they put a couple of arrows kind of pointing to those different regions, right? As you oxidize, you see that this is the little ring structures, or the disordered part seems to be going away. So you can get oxidation of particles so particles that are really small can actually oxidize from the inside, but particles that are larger, that are mature, can actually, let me go. See that, so here's another one that's where you have a bigger particle, and it's immature. You have the graphene sheets, right? The polycrystalline graphite on the outside, and those are now oxidizing from the outside. So these are large, mature particles. Small, mature particles can oxidize from the inside and also from the outside, and not mature particles tend to oxidize from the inside. So I think that's actually really cool. And it's probably a matter of the oxygen being able to filter into the center of the particle and get to the more reactive part of the particle. And if the particle is big, it's probably harder for the oxygen to get in, but it takes a higher temperature to oxidize these more mature sheets of graphene. So I think that's actually really cool. And so you see on the upper right-hand side, what they see is you probably pull off individual oxygens, and you start to flake off parts of your graphene sheets, your polycrystalline graphite sheets. So I don't know. I guess I love these studies where you can actually see, you think you know what's going on, and they actually can see it in an image. It's really makes me excited. Okay. Oops. Yeah, and this is an old study from 1984, and this is a study that indicated that you can also have oxidation that breaks your aggregates apart. So if you think about it, remember how you're holding your aggregate into primary particles by these graphene sheets just are going over the outside? If you start to oxidize the outside of the particle, that those primary particles may not be so connected once you break away those bridges, those necks, right, in the particle. This is from Seraphim's group from 1984, showing this kind of fuzzy. At the bottom is your aggregate, and at the top is after you've oxidized it. So let me show you actually a newer one that has a similar type of technique, where you can see a little bit more clearly. So this is from Joanne Leidy's group. And you see that how they did this experiment is they had two burners. So they had a lower burner that was burning rich and generating soot particles, okay? And then they had, and they're generating mature soot particles. And then they had an upper burner that was burning lean. And they sent the soot particles from the first burner into the upper burner to see if they could watch the oxidation of the particles. So they looked at this with scanning mobility particle sizing, and you see that on the right hand, on the very furthest one where it says case 1, you have a large size distribution. So the x-axis on here is the mobility size. The y-axis gives you the size distribution, so the number of particles in a particular size bin. So, and then as you go up in that second burner, so this is height above the second oxidizing burner, you see that you start to get a small fraction, right? A second peak starts to grow in at smaller sizes, and they interpret this as the particle starts to break apart and generate small particles. This is a very nice study. Showing that as the particle, the big particles go away and they generate small particles, and then those particles oxidize away. And I think they can get rates from this, this study to figure out how fast you're getting those particles to go away. Okay, so we can see when we do Sachs measurements without sampling from the flame, we can actually look at oxidation rates. And we see something similar just by doing, so we have our X-ray probe sending it into the chamber, into our flame, and we detect the angle at which we scatter. So that allows us to get the size distribution of our particles. So low in the flame, so this is going from 5 millimeters up to 9 millimeters. The height scale is actually on the left-hand side of the graph over here. Remember, at 5 millimeters is where we're starting to see mature soot and kind of the highest volume fraction in our LAI measurements, right? And we see a nice size distribution. The Sachs measurements are the purple curve, and then the bins that distribution is from transmission electron microscopy when we extracted. Remember, we looked at TEM. That's from the TEM. And you notice then as we get up to 8 millimeters, that's where the LAI signal is going away, right? That's where the Sachs signal is going away on the volume fraction. And what we see is when we run this model, we have to put in a second mode this small once we get to that height. I didn't expect it actually. I was having a really hard time fitting the data, and the only way I could get it to fit is if I put a smaller distribution size. And then I was like, oh yeah, duh, of course it should be there. So you see as you go up in height, you have this small size distribution, and that's without extracting. So that's like, yay, success. But we can't see that with TEM. We can't see those particles. They're too small for us to catch. We just can't catch them, okay? So I think probably if we did SMPS, we could see them. Yeah. Okay, so that's... So here's another study showing in one of these machines from the same group, from the same paper actually, showing fragmentation of the particles in the TEM, in the environmental TEM machine, right? So you start out, that A is one section of that aggregate, and you can see where the next are getting eaten away and the aggregates are breaking apart. So you can actually see why this fragmentation is happening. And you start to fragment into just these smaller pieces. Yeah. Okay. Yeah, here's another one showing the neck actually going away. So if you go from left to right, you can see where your oxidation is occurring. And they say when they do these studies that it seems to preferentially go for these necking regions. I'm not sure why, but they seem to be more reactive than the actual regular primary particle coating, like polycrystalline graphite coating. Okay. I'm going to skip this guy. Yeah, we looked at our XPS measurements also seem to indicate that oxidation occurs on the surface. Oh yeah, okay, so what's the composition now of the particles as they grow? So we can do aerosol mass spec, but so what starts to happen is our signal starts to go away, right? As you get more mature, you're not gonna get those things vaporizing off your surface. And what we see for the average size of the species is, as we're growing the particles, the average size of the species of the mass spectra we see goes down, and then it goes back up again. So the average size decreases and then increases. So you can kind of see this in the mass spectrum. See, at 3 millimeters, it's kind of like almost at the minimum, and then as you go up to 5.5 millimeters, you see it increases. So let me just show you what other people see. Because this is kind of a fascinating area. Okay, so what we see is the total ion signal increases and then decreases. Like this is the same burner, right? Oh no, this is a premix burner. The last one was the Henkin burner. This is a premix burner, very similar to some of the other results I'll be showing you. And then the average mass goes down instead of going up. So it's opposite in the premix burner than it is in the diffusion burner. Okay, so this is kind of interesting. So this is should be starting to get your thinking going. It's like, okay, what's going on? What's happening here? Okay, and this is actually really common, this distribution that we see as we go up in the flame. The size, we get these big peaks that just seem to grow in. This 202 and 226, I don't know, they just always grow in. Haven't figured it out, so if you're thinking about what's happening, this is a good thing to think about. And it's not just us, a lot of people see this when they do aerosol mass spectroscopy. Okay, so that's premixed ethylene. The same thing happens in a methane flame, right? Very similar type of results. The average mass goes down. Okay, but remember, the average mass went up in the diffusion flame. Okay, this is a controversial result, okay? In that, this paper came out recently, and notice that these species are huge, right? They're much larger than I was showing you in our aerosol mass spectra, right? So this paper was written and it says, okay, soot is forming by nucleation. The species are large enough, maybe no one else sees them, but they're there and we see them, and the species are large enough to nucleate. No question, boom, it's over. We figured it out. Soot is nucleating by large species just coming together by dispersion forces in the flame. None of this chemistry stuff, none of this radical stuff matters. It's only you have big species. So I'm here to explain why they see this. Okay, so what they see is this result, but notice where they take the result. And you actually, if you read this paper right now, you'd be able to spot this too, because I've given you all the information and you've been thinking about it. I can see your faces concentrating and figuring this out. Okay, this is a diffusion flame. They made the measurements on the edge of the flame where you have, what do you think you have on the edge of the flame where you have laser-induced incandescence? They see very strong laser-induced incandescence. Who said that? Who said? Mature soot. Right, exactly. Hannah said mature soot. You have mature soot. So if you're making a measurement looking at mature soot, are you looking at inception? No, you're not looking at inception. And what happens when in a diffusion flame to the average mass of the species? Increases, right, it increases, yes. So I think what they're seeing is they're actually seeing mature soot that's, one, it could be mature soot, but two, think about this. We just talked about oxidation. What's happening when you oxidize mature soot particle in a high temperature? You're fragmenting stuff, right? You're getting flakes of stuff coming off the surface. I think that explains these results. It's not that you have big species that are going to nucleate, okay? So I may be completely wrong, but that's what I think is happening. So if you see this result, think about it, and maybe you can come up with another story. Okay, good job, good job. You're paying attention. Hey, okay, oxidation mechanisms. Here's a couple of oxidation mechanisms people talk about, right? There are different types of oxidation mechanisms. How do you can oxidize with O2, you can oxidize with OH. You're grabbing these carbon atoms, on the edges of these things, these sheets, maybe in the center, you're fragmenting, they're falling apart, they're flaking. I gotta make sure I don't go over. Okay, so that's our oxidation. I think, yes. Okay, let's quickly start okay, so does anyone have any questions? Yes.
So, just out of curiosity, you said that it has preferential treatment for the, because the surface area to volume relationship?
So the question is, I'm going to repeat it, is it, so we preferentially oxidize on the bridges, and maybe that's because the surface area to volume is higher, so we're oxidizing those surfaces. That could be, or another explanation is the necks may be more curved and may actually have more strain. Like, maybe they're, have, when you have, so oxidizing some of these curved species actually is easier than oxidizing a flat, all 6 membranes. So maybe your explanation is right. I don't really know actually why but that's a really good question. Yeah.
On that, do we have any idea of the temperature distribution of agglomerations and the as a whole? Because surely hot spots, inside there, which may give.
Yeah, so the question is, is there a temperature distribution of the soot particles themselves within, are they homogeneous temperature, right? Yeah, could you have an inhomogeneous temperature distribution of the particle itself? Usually, so I'm gonna say that even when you're heating particles up with laser-induced incandescence, when we calculate this, when I calculate how fast and I use heat conduction equations for along the basal plane and then perpendicular to the basal plane, I calculate that it should take about 6 picoseconds to heat through a particle, primary particle. So I doubt it, but you never know because you'd have like conduction preferentially on the outer particles, and who knows, there may be something going on that we're not accounting for. Yeah. Yeah, thanks for the questions. So I saw another hand up. Yeah, Sodervin. Yeah. Yeah.
At that stage, where are those oxygen coming from?
Oh, where are you getting the oxygen? Yeah, so the question is, if you're trying to oxidize mature soot, where is the oxygen coming from? If you're in if there are going to be conditions, so you're asking if you have a condition where you don't have oxygen, what's happening? You're not oxidizing, right? So in these cases where we see oxidation, it's because we're in a diffusion flame, and you have air flowing, and at the surface where you have the most mature soot, that's where you're having oxygen diffusing into the flame. That's where the oxygen's coming from, yeah. And in the environmental TEM, they add oxygen. Yeah. Those are great questions, thank you. Oh, so, okay. And so are there any more questions? Okay. So we have like 5 minutes and then we'll take a break. And I'll just start getting going on our next topic. Okay. Okay, so we'll be talking about, so we'll have, in this section, we have a lot of diagnostics that are available to us. Some of them are ex situ, so we have to extract particles from the flame and then maybe process them, maybe put them under vacuum, there are a whole bunch of things we can do with these particles. There are a lot of material science diagnostics that are available to us. So we'll start out by talking about, anyway, I'll get this going during break. So there are a lot of diagnostics we can talk about for ex situ. And then I'll talk about sampling. So in order to do these ex situ diagnostics, we have to do some kind of sampling. And sampling it alone is a real problem because you have a really reactive environment. Once you put say like a quartz tube or a metal tube close to your flame, you're going to start to perturb the flame itself. You're going to perturb the radicals are going to start to react with the surface. So you're going to have a change in the radical distribution. The temperature, you're going to have temperature changes because of the probe. So there are a lot of different things will happen. We'll talk about sampling, and then maybe there are ways of getting around sampling, and that's another challenge we have, is like how do we get around the sampling issues? Because there are a lot of diagnostics we really want to use for sampling. With sampling. And then I'll talk about in situ diagnostics, where we can, usually it's either laser or X-ray that we can actually probe the flame or the reactive environment, not just flame. I mean, there are other cases when you're trying to synthesize particles and you have a very reactive environment, you don't want to be able to don't want to have to sample. So are there ways that we can do some of these diagnostics? So I spent a good part of my career actually trying to figure out ways that we can do this. So I'll talk a little bit about that and what all the problems are associated with them, and how we can get around those. And so that will be kind of like our diagnostics section, and then after that we'll move into, not today, but tomorrow, we'll move into atmospheric effects of particles and how we, like what are the issues, and how do we, like what are the things that we need to understand in order to understand, say, impact on climate, and then that brings up a whole host of things we also don't understand. So how about if we take a break? Oh, let's just take a break now. Like it's 2 minutes anyway, and then I'll see you in 15 minutes or at 4:30.